right, this is a video to review trig and geometry for finding angles, especially as regards to static equilibrium and torque problems, but I'll just do kind of a general review of these concepts to help you remember how to apply them. So the first thing I want to remind you is that if you have a right triangle like this, we've got two angles here, theta and phi. It's always true that the angles in a triangle sum to 180 degrees. So sum of all the angles equals 180 degrees. And if you have a right triangle, then one of those angles is 90 degrees. Which means that your remaining two angles, which here I'm calling theta and phi, sum to 90 degrees. So let's talk about an example. So for example here, if this angle at the top is 20 degrees, if I want to find this angle theta, theta plus 20 degrees equals 90 degrees, so I know that theta equals 70 degrees. Okay. Now, another important concept to remember that's generally true is that similar triangles have the same angles. So what do I mean by similar triangles? So similar triangles means they're the same shape, even if they're of different size. So for example, if I have this triangle to start with here and say, I labeled this one. This is fine. The cartoon and the previous one, the angles don't really make sense, but the numbers are right. That angle that I labeled as 20 looks more like a 70-degree angle, but that's okay. All right, so here I'm going to call this angle 80 degrees, which makes this angle 10 degrees. Now I can draw a similar triangle here. So this similar triangle that's in purple has the same shape as the blue one, even though it's a different size. And that means that its angles are the same. So this angle here in my purple triangle is 80 degrees. This angle here in my purple triangle is also 10 degrees, okay? And that's often helpful. You can often draw an angle that's similar shape. Okay. Now the next thing we want to review is how to use our trig functions. So let's draw another triangle here. Let's say we know that this angle theta is 25 degrees. And say we know that this side is 5 meters. And we want to know what's the length of this side here. And what's the length of this side here. And actually, yeah, that works. So your SOHCAHTOA can be helpful for remembering this, or however you remember sine and cosine functions. So if we want to know the angle A, in this case for this theta, A is our opposite side. I'll label these all in a different color. So we've got our opposite side for our angle theta, our adjacent side for an angle theta, and our hypotenuse for our angle theta. Okay. So if we want to find A, we know that A over 5 meters, it's opposite over hypotenuse, is sine theta. Now, some of you may be bothered by the fact that this A, which is in the x direction, I used sine to find it. Okay, but again, it's the geometry of the triangle. But if it makes you happier if you like it better if you use a different angle, that's fine. So you can always do that. Oh, let me pick a color that's more colorblind friendly. So I'll pick magenta here. So if my angle theta is 25 degrees, we know that phi plus 25 degrees equals 90 degrees, and my angle phi then is going to be 65 degrees, okay? And I can use this just as well with my trig functions, but now all these sides need a different label. So my adjacent side is now the one next to my angle. My opposite side is now this one, and my hypotenuse is now this one. So now if I want to find phi, I'll find that a over 5 meters is cosine of phi. So either of those are just as good for finding that angle, okay? And then one other point that I want to make is that if I've got theta here, I've also got this other angle here, which I'm going to call theta prime, okay? And we know from geometry that theta plus theta prime is 180 degrees. So you can find this inner angle or this outer angle from the same one. Now, say that we know the length of this hypotenuse and we want to know the height of this triangle. All right, we can use that height is the hypotenuse times sine theta. It's also the hypotenuse times theta prime, okay? Times sine of theta prime, excuse me. So in the most recent video where there was the problem with the light hanging, they used this exterior angle instead of the interior angle, and that was confusing for a number of students. But those both have the same sign, so either either one of those is totally acceptable. Okay, but cosine would be different because they'll have a different sign with a SIGN. So for cosine of theta is going to be here in this direction. It's going to be the other direction for theta prime. So you don't want to use cosine either direction this way, but sine can be used in either direction that way. Okay. And let's do one example where we connect this to torque. So if I imagine a bolt and a wrench, and I want to know the torque on the bolt from this wrench. So imagine that I apply a force like this. So remember our torque formula, we have 3 different ways of calculating it. We can calculate R, F, sine theta, where theta is the angle between R and F. We can say R times F perpendicular, where F perpendicular is the magnitude of the force, the component of the force that's perpendicular to the radius. Or, and these are really magnitudes. Or we can say that our torque is the perpendicular component of the radius times the force. So that's the component of the radius that's perpendicular to the force. All of these give us the exact same answer. So let's take them each in turn. Let's start with this first approach. So I need to start by drawing my R vector from my axis, which in this case is my center of my bolt, to the point where I'm applying my force. And then I'm going to find the angle between them, which I'm going to use this angle here. You can also redraw your R vector over here and use this angle here, theta prime. Either of those are just as good, okay? So we can calculate RF sine theta that way, okay? Now let's talk about the second one. How do we use the perpendicular component of our force to calculate our radius. Sorry, our torque. So now we want to calculate find the perpendicular component of our force, and that means perpendicular to the radius. So we can imagine our force vector as having two components. One like this, that's perpendicular to the radius, and one that's parallel, right? In other words, we've drawn a coordinate system where we can think of X and Y, or we could label this as parallel and perpendicular. So parallel to the radius and perpendicular to the radius, okay? Now, this here, it may be easier to think of it on this side. So I'm going to draw it again on this side. If I draw it on this side, you can see this angle theta is opposite this perpendicular side. So this is my F perpendicular component. This is my F parallel component. Let me highlight each of these. So I'm going to highlight parallel component in orange here because we're not going to use it. And then my perpendicular component, I'm going to highlight in like this to match the color here. Okay. So the magnitude of that F perpendicular is F sine theta. Okay. So this second approach, if I plug in for my perpendicular force here, I've got F sine theta. So the same thing I found in the top. And I've used sine theta prime over here, but those are the same, remember? So sine theta and sine theta prime are the same, okay? And then our last way of doing this is a little bit more complicated, perhaps. I'm going to actually draw my picture again down below so I don't get as cluttered. So I'm going to draw my R vector again and my F vector again. And then I want to find now the component of my R vector perpendicular to my force. So when I say the component perpendicular to my force, I can imagine drawing a coordinate system now here, where now this would be parallel and this would be perpendicular. Okay, I've drawn a coordinate system parallel with this vertical here, or sort of vertical, is parallel to my force, and this one is perpendicular. If that's confusing, it might help to turn your paper or turn your head sideways, or draw this on your own paper so you can turn your head sideways, okay? And now I can draw my R vector as having components along each of those directions, just like we did above. So here, this is my R parallel to my force, and this is my R perpendicular to my force, okay? Now, the geometry here is maybe a little bit confusing because maybe it's not obvious how we find an angle for that. So remember, we knew that this was theta. Well, now if we look at this straight line here, that means that this angle here is theta prime. And by theta prime, I mean 180 minus theta. Just like up above. If you look at this, you'll see that really it's the same pictures up above, okay? Just like we knew that the complementary angle was the one in the line before, okay? So now I want to find this R perpendicular component, and I can find that R perpendicular is R sine theta prime. Again, because it's opposite of my angle, okay? All right, and that's my summary. I'll post these notes along with the video on Moodle.